G'day everyone. In this video we're covering a question that I saw posted on a maths Facebook page, also on my integral page. I'll put a link to the Facebook page that I run on integration in the comments. If you want to jump on there and have a look, you're more than welcome to. But anyway, we can see it's a fairly simple looking integral, and thankfully just with a couple of minor steps we can actually resolve this one using the beta function and then by extension the gamma function. And thankfully this situation in particular, with the restrictions that were given to us in this case on A, allow us to employ Euler's reflection formula. Okay, so let's dive into it. The first thing that I've done is we take the integral as it is, the integral from negative infinity to infinity of e to the ax over 1 plus e to the x dx, and all I've done is just employed power law, indice power law, and all I have done is separated out the a and the x, so just very basic indice laws there. And the reason why I've done that is because I want to make a substitution of u is equal to e to the x. So when I first looked at this, I went, this looks very, very similar to a form of the beta function that I'm familiar with, but instead of having the e to the x, it's normally a u or a t or some single variable. So that's what I wanted to try in this case, and you'll see that that is the substitution that we make in the next step. So u is equal to e to the x, which means just equal to e to the x, which equals u. And so we have dx, just rearranging this, if we bring the dx up to here, we've got u dx and then divide it through. We have dx is equal to 1 over u du. So we know that we're going to replace this with u, we're going to replace this with u. This is now going to be replaced with 1 over u du. And so the last thing that we need to do is just transform our bounds. So at the lower bound, when x is, equals negative infinity, or should I say as x goes to negative infinity, we have u is equal to e to the x, so u is equal to, or u approaches e to the negative infinity, which is just equal to 0. And then for the upper bound, x is equal to infinity, or better put, as x goes to positive infinity, we have u equals, or u goes to e to the power of infinity, or it's going... Yeah, the limit is that it's going from e to x as x goes to infinity, which obviously, because e is a positive number, this is just infinity. So our lower bound is going to be replaced with 0, and our upper bound is going to be replaced with infinity, or it's going to maintain itself as infinity. Okay, so let's sub that in. We've got I of a, which equals the definition as we had before. Remembering, e to the x is getting replaced with u, so we have u to the power of a over 1 plus, my apologies, this should be u, not a. And then where we have dx, that needs to be replaced with what we have here, which is 1 on u du. So we've got a u to the a here, we've got a u on the bottom here. Obviously that just then becomes u to the a minus 1 over 1 plus u. So just remember, this a should be a u. Okay, now this is a very common form of the beta function. This is the form that initially made me think, oh, I think we can apply the beta function here. So one form of the beta function for x and y, where x and y, the real components have to be greater than 0, is the integral from 0 to infinity. Oh, and again, sorry, I just want to clarify something really quickly. I just said the condition is that the real parts of x and y have to be greater than 0. That is because the beta function can be defined in terms of the reals or within the complex. I'm only going to deal with a real base interpretation here, and I'm doing that because, I'll be honest with you, my complex analysis isn't as great, so everything that I'm doing at this stage is going to be real base. And on top of that as well, our parameter a is a real value. So we're just going to deal with the real restriction, and the real restriction is that this parameter x and y both have to be positive quantities. So anyway, the form is the integral from 0 to infinity of t to the power of x minus 1 over 1 plus t to the x plus y dt. So if you have a look at what we've got, this is just a form of it. We can see the top part is really easy to see. X minus 1 equals a minus 1, so we have x is equal to a. And what we need on the bottom here, we've got 1 plus u, or 1 plus t, doesn't matter obviously, to the power of 1. So we need our x plus y to equal 1. We have x is equal to a, so we need a plus y to equal 1. Rearranging that, that just means that y is equal to 1 minus a. And so therefore, I of a, our integral from 0 to infinity of u to the power of a minus 1 over 1 plus u du is equal to the beta function evaluated at x is equal to a and y is equal to 1 minus a. Okay, so the next thing that we're going to do is we're going to use the relationship that exists between the beta function and the gamma function. Beta function of x comma y is equal to gamma of x, gamma of y over gamma of x plus y. So therefore, I of a, which equals beta of a 1 minus a is equal to gamma of a times by gamma of 1 minus a over gamma of x plus y, which is a plus 1 minus a. Obviously the a's just cancel out, and we're left with gamma of a, gamma of 1 minus a over gamma of 1. Gamma of 1, which is 0 factorial, is just equal to 1. And so we're left with gamma of a times by gamma of 1 minus a. Now here, this is a very special form, and this allows us to use Euler's reflection formula when it's applied to the gamma function. And so the rule is gamma of z times by gamma of 1 minus z is equal to pi over sine of pi z, and this is valid when z is not an integer quantity. So in our case here, we've got this exact form, obviously, but we've got a instead of z. I mean, who cares? Now, a in this situation, as was given to me in the question, is a parameter between 0 and 1. It's not, and it doesn't allow for 0, and it doesn't allow for 1. And so therefore the restriction that we have in using Euler's reflection formula here in this special form is satisfied, because remember, it is that z is not an integer. Well, za, our value instead, is not an integer, so that's satisfied. So therefore I of a, which is equal to this quantity, gamma of a times by gamma of 1 minus a, equals pi over sine of pi a. And so therefore, I of a, which is the integral from negative infinity to infinity of e to the ax over 1 plus e to the x dx, is just equal to pi over sine of pi a. And that's our solution. So this one, obviously, a very simple one. Want to give a big shout out and thanks to the person who I saw this question on. I'm not going to mention that gentleman's name because I haven't sought his permission, but thank you very much for the question. I enjoyed doing this one. And as I say in all of my other videos, well, firstly, if you like the video, please like. If you'd like to see more videos of this nature, please subscribe. If you have any requests whatsoever, please either direct message me on the Facebook page that I'll have the link at, or alternatively direct message me on YouTube, and if I can solve it and I have time to be able to do it, I will certainly post it up. I will definitely get back to you and let you know in either case. Otherwise, I will see you on the next video. Okay, goodbye.